More definitions incoming. For each subset S of Z, we define what I'm going to call the shade of S to be the subset, and here is my notation for it. Take some getting used to S minus 0 plus, but you will see why. It's the union of S itself with S shifted by 1 to the left, so the set of all S minus 1 for S and S, and S shifted by 1 to the right. Let me give one more description. This is the set of all integers I, such that at least one of I minus 1, I and I plus 1 belongs to S. And another way to say this is all rooms that are occupied or adjacent to an occupied room in S. So if I'm trying to mark the rooms in S with a very thick brush, and every time I mark the room, it bleeds over into the two adjacent rooms, then I get this shade set. So this is why I call it S minus 0 plus. So this stands, there are 3 copies of S in there. This is the 0 copy, which is just S. The copy where you shift it all to the left by 1, and the copy where you shift it all to the right by 1. That's this minus and the plus. So note that S, of course, is a subset of this shade, and the size of the shade is at most 3 times the size of S, because the shade consists of 3 copies of S. If the copies overlap, the size is smaller, otherwise it's just equal to 3 times the size of S. Now, why do I need these shapes? Here is the reason. It is not usually true that the states have this relation where every state is a subset of the next state. This would mean, so let me restate it as follows. So it is not true that the states keep increasing, because occupied rooms can become unoccupied when their tenants move out. Yeah, that would be too nice if they would always remain occupied. However, we have basically the same relation holds for the shades. In other words, if a room is occupied, it doesn't mean that it will always be occupied. However, if a room is occupied or adjacent to an occupied room, then it always will remain occupied or adjacent to an occupied room. So if you don't just look at occupied rooms, but you look at the shades, you look at the occupied or adjacent rooms, then you have this relation. If it once has this property, it will always have this property. Let me restate this as follows. We have Si, the shade of Si is a subset of the shade of Si plus 1 for each I in 0, 1 to G minus 1. And again, you do it. It's not difficult, because all you have to do is you have to argue that if a room is occupied or adjacent to an occupied room, then after one move later, it will still be occupied or adjacent to an occupied room. This is a matter of distinguishing all possibilities for what the move could be and checking that it's true in all of them. So claim 3, as we said, yields this relation. All right. Now I've said that the sets have minima and maxima. Now I'm going to use this at last. So let alpha be min as 0 and omega be max as 0. So if I look back at this example, S0 is the initial state. Alpha is the leftmost room that's occupied, and omega is the rightmost room that's occupied at the beginning. So it's the initial state. And now this is crucial. Next claim. Let M be between 0 and G, then min Sm is bigger than alpha minus 3n. What does this mean? We have seen on this example that the leftmost occupied room doesn't have to stay the same. Sometimes, for example, here it moves left. And again, here it moves left. What my claim here is saying that it will never move more than 3 n steps left. Actually, it will never even move 3 n steps left. So this is what it's saying. The leftmost occupied room will always be bigger than alpha minus 3n, or to the right of alpha minus 3n. And this is a matter of looking back at these old claims. So I will have to say a few more words about this. This is kind of crucial. So how does this work? So consider the sequence. So basically consider what happens to the leftmost unoccupied room between S0 and Sm. Claim 2 shows that every time two violinists move apart, the leftmost occupied room either stays the same or moves left by 1. So claim 2 shows that each entry of the sequence either equals the preceding entry or equals the preceding entry minus 1. Hence, if mean, okay, let me word this as a proof by contradiction. So we assume the contrary, so this minimum is less or equal to alpha minus 3n. And now if I look at the sequence, its first entry is alpha, and its last entry, as we just have seen, is at most alpha minus 3n. Hence, because this sequence contains alpha and a number less or equal to alpha minus 3n, it must also contain all the numbers between alpha minus 3n and alpha. Because since you have this property that each entry is equal to or the previous entry or z minus 1, the sequence cannot jump over any number. If it starts here and it goes down to here, it can only achieve this by going down by 1 step. It cannot jump through any number. Therefore, all the numbers between alpha minus 3n and alpha must belong to the sequence. Hence, so let's rewrite it. Every integer j in the interval alpha minus 3 and alpha must have the form minus sk for some k. Minimum, not minus. Hence, now a minimum of a set always belongs to that set. So if it's a minimum, it must belong to sk, thus also to the shade of sk, because a set is a subset of its shade. And thus also to Sm minus 0 plus. Why? Because the shades of those states keep growing. So if it's in a shade at some point, it will always be in a shade after any moves. Thus, we have seen that each integer between alpha minus 3n and alpha must be in the set. So the set has at least 3n plus 1 elements, because there is 3n plus 1 integers in this interval. 3n plus 1 integers, j in this interval. However, this is just not true. The shade, as we have seen above, is at most 3 times as large as the set itself. And what is the set? The set is the set of all occupied rooms. It's just, the number of occupied rooms is the number of violinists, which is n, so 3n. And this is not bigger than 3n plus 1. This is less than 3n plus 1. The two previous preceding sentences contradict each other, and claim 4 is proved. if you look into my notes, I'm doing it a little bit more complicated because I want to use a bit less of claim 2. So I have to do a bit more in this proof. But the idea is the same. Okay, so we have bounded the leftmost occupied room. We basically say there is no way the violinist will ever go left of alpha minus 3n. Now we can do the same on the right. Let me just copy paste it. Instead of looking at the leftmost occupied, I look at the rightmost occupied room, and now the bound is omega plus 3n. Proof of claim 5 analogous to claim 4. And now it's time to combine these things. I claim that Sm is a subset of this set that be alpha minus 3n plus 1, alpha minus 3n plus 2, alpha minus 3n plus 3, alpha minus 3n plus 4, and so on to omega plus 3n minus 1. And this follows from claims 4 and 5. I leave you the details. What is important is that this is a finite set that does not depend on Sm. It only depends on the starting state. Alpha is the leftmost occupied room at the start, omega at the rightmost, n is the number of violinists. This is might be a big set, but it's a finite set. So we have shown that every state we ever obtain is a subset of this here. I mean, we ever obtain from our starting state. But this set is finite and thus has only finitely many subsets. Hence, there are only finitely many states we can possibly obtain from our starting state. Hence, so therefore, there are only finitely many possible entropies that our states can have. And since we know from claim 1 that the entropy increases every night, so with every move apart, we thus conclude that the moving must stop because it cannot keep increasing forever. There is only finitely many values that can go through. At some point, it will have run out of possible values. Exercise solved. And again, if you look in the notes, I am a bit more precise there. I am actually giving a bound on how many moves you can make. But that's the obvious bound. I just take the number of subsets of the set, and this is how many moves you can do at best. It's far from an optimal bound, but it's a bound.